To complete the construction of our frequency distribution for the drive-through service times, we are using 6 classes with the class limits and class width as established in the previous video. Now, I left the tally column out here because, to be honest, to sit here on a video and go through one thing at a time is a little bit ridiculous. And second of all, because honestly, we rarely ever use it in this day and age of computers. If we can load the data into a spreadsheet like it's in Excel, we can actually have the computer sort the data for us in order. I will show you how to accomplish that as we move forward in future lessons. But for now, we'll take the data set as having been sorted, and what you can do is actually simply just count up how many numbers are there from 83 to 120, and it's very simple when they're in order because you just count up the numbers until you hit something that's bigger than 120. In this data set, and if you want to follow along by tallying, or if you know how to sort the data and count it up yourself, as it turns out, there are 10 data values between 83 and 120. There are 20 data values between 121 and 158. There are, again, 10 data values from 159 to 196 seconds. In the next class, there are 5 data values, and then 3, and then 2. Now again, in the description of the problem, we are told that this is a sample of 50, but it's always a good idea to just double check the sample size by adding up our frequencies. Especially because if we are doing this with the tallies, or if we are doing it by having the computer sort it, you never know, we might miss a number. It's happened before, it's happened to me. It can certainly happen to anybody else as well. But as long as they all add up to 50, which in this case tends to be easy to do, 5, 3, and 2 together is 10, and another 10, and a third 10 is 30, plus 20 is 50, then we can be reasonably sure that we've accounted for all the data values and that we haven't left any out or double counted. Now, we can still find the relative frequency. Of course, the relative frequency refers to the percentage of data values that are now within this range of values that are in this class. But the concept is still the same. We take the frequency of that class and divide it by the sample size. Now in this case, we are lucky enough to have a very friendly sample size, and that results in very nice decimals. We continue on. 20 over 50 is 0.4. 10 over 50 is again 0.2. 5 out of 50 is 0.1. 3 out of 50, 0.06. And 2 out of 50, 0.04. Once again, it's a very good idea to sum these up because the answer should come out to be 1 or something very, very, very close to it. In this case, no rounding was necessary at any point, so this should add up perfectly to 1. Well, 0.2 and 0.4 is 0.6, and another 0.2 is 0.8, and a 0.1 is 0.9. Plus this would give us 0.96, and then 0.04 more would give us 1.00. So, perfect. We got the right counting, we got the right relative frequencies, everything adds up the way it is supposed to. Frequency distributions are fairly simple in what they do and their basic structure. The trickiest thing is, again, constructing the classes. And the two parts of that are trickiest are remembering to always round up the class width no matter what, even when it's a whole number. You always round up. And second, that the class width actually is the difference between successive lower limits or between successive upper limits. And that saves, if you do it like that, you can construct the classes accurately and quickly. Now, there are other ways to construct frequency distributions. Sometimes they are done with much more friendly values. I think we could all agree, looking at this now, that starting with 83 and having to add 38, again, doesn't produce the nicest value, and then adding 38 again, none of these values are particularly nice to be working with. So there is a school of thought that says, well, maybe we'd like the numbers to be more presentable. We'd like them to look nicer. So there are times where we might choose to have the first class start at a friendlier number, like say have it start at 80, because 80 is just nicer. That gets a little bit tricky because we want to make sure that, again, the classes follow the rules. They all have to be the same size, they all have to be mutually exclusive, but they also have to be continuous and exhaustive. Every number needs every data value needs to fall into exactly one class. We cannot leave anything out. So we run into a bit of an issue if we knock down the starting value there and try and make everything friendlier. We may run into an issue where the last class we get into a bit of a problem. So this is the most unbiased way to construct a frequency distribution with grouped data.